airfield can fail for many reasons, but sometimes the difference between runway and wreck comes down to one physical limit. For work number 0880119, it was the load-bearing strength of winter ice. This aircraft is a Junkers Ju-88A1, a tactical bomber marked with the code U4+TK. It does not lie in a debris field scattered by high-velocity impact. It rests largely intact on the bottom of a Norwegian lake. What follows is not a story of pilot error or an in-flight breakdown, but of a static load limit quietly crossed as the season changed. In April 1940, the German invasion of Norway, Operation Weserübung, ran into a hard logistical reality. The Luftwaffe intended to anchor its operations at Værnes, but the field was in poor condition and lacked a paved runway. To keep aircraft moving in the Trondheim area, the Germans turned to an improvised solution: the iced surface of Lake Jonsvatnet, used as a temporary air station. The entire plan rested on one promise: the winter ice could carry the load. The Junkers Ju-88 is a heavy machine. In its operational configuration for the Norwegian campaign, the aircraft carried a loaded weight of approximately 26,000 pounds, roughly 12 metric tons. This mass is supported by two main landing gear struts. On a concrete runway, this load is routine. On a floating ice sheet, the physics of support change entirely. The ice does not support the aircraft through rigid compression alone. Instead, the ice sheet acts as a displacement membrane. When a 12 metric ton aircraft rolls onto the ice, the sheet deflects downward, displacing the water beneath it. The buoyancy of the displaced water pushes back against the ice, creating the support force. For that promise to hold, thickness was only the entry requirement. In April 1940, the ice at Jonsvatnet was reported at about 1 meter thick, roughly 3 feet, enough to take heavy aircraft at first. But the real margin lived in the ice itself. Temperature, cracking, and internal bonding determined whether wheel loads could spread outward through the sheet instead of punching straight down into water. Early on, it worked, long enough for Luftwaffe crews, often identified in secondary records as Ergänzungskampfgruppe 4, to launch and recover sorties from the lake surface. The operational timeline was interrupted by events on and beyond the front line. By late April 1940, the Luftwaffe was already thinning out the Jonsvatnet detachment as the ice began to soften and crack, and as work accelerated to make Værnes usable. Aircraft that could no longer depart safely were stripped of valuables, fuel was drained, and the airframes were left behind on the ice. Then temperatures moved above the freezing point, and the bearing capacity of the improvised airfield began to collapse from within. As the sheet warmed, the bonding between ice crystals weakened, reducing tensile strength and the ability to distribute a 26,000-pound load. The deflection bowl under the landing gear deepened until stress exceeded the shear strength of the decaying material. The failure was not violent. The ice gave way, and the aircraft slipped through the surface. There was no violent crash sequence. Once the ice failed, the bomber simply slipped beneath the surface and sank through the water column, settling onto the Lakebed at a depth of roughly 74 meters, about 240 feet. Because the loss occurred due to static failure rather than ballistic impact with the ground, the airframe arrived on the bottom with its major structural components united. The fuselage, wings, and empennage remained in their aerodynamic configuration. The aircraft was effectively parked on the silt. For 64 years, the bomber remained in this position. The location was known, but the depth placed it beyond the reach of casual recovery. Detailed searches and planning resumed in 2003, and the lift operation followed in late August and early September 2004. This was not a hunt for a missing plane. It was a precision recovery of a known object, an attempt to bring the aircraft back into daylight without breaking the structural continuity that had survived the descent. But while the cold water had spared it the violence of a crash, the lake environment had still been working on the aircraft, slowly and selectively, year after year. Around the 4 degrees Celsius mark, the deep layers of Lake Jonsvatnet tend to hover near the density point, shifting by a few degrees as the lake mixes in spring and autumn. In that cold band, the submerged Ju-88 was buffered from rapid seasonal swings at the surface. While the ice failure in 1940 initiated the loss, It was the combination of depth and low oxygen conditions that shaped what could be recovered decades later. Down there, the wreck enters a zone of physical stasis, radically different from a terrestrial crash site or a saltwater wreck. The descent of the aircraft was governed by fluid dynamics rather than gravity alone. When the machine slipped through weakening ice, it may not have dropped like a stone. The Ju-88 is a broad shape with a wingspan of 65 feet, and in water that surface area can create drag and a slow, arcing descent rather than a straight plunge. That kind of fall bleeds energy into the water column. It does not guarantee a gentle touchdown, but it can help explain why the final contact with the lakebed reads less like a high-velocity collision and more like a heavy object settling into soft silt, with the landing gear and ventral gondola gradually sinking into the bottom. Once the aircraft came to rest, the physics of the loss were replaced by the chemistry of preservation. This is the mechanism of the freshwater time capsule. In a saltwater environment, the ocean acts as a highly conductive electrolyte, accelerating the oxidation of metal through rapid electron transfer. Chlorides in the water aggressively attack aluminum, converting the skin of an aircraft into white powder within decades. In the deep freshwater of Jonsvatnet, this electrolytic potential is absent. The water contains very low dissolved oxygen and almost no salinity. Under these conditions, the aluminum alloy of the aircraft skin forms a microscopic, stable oxide layer that seals the metal from further degradation. This passivation layer acts as a permanent shield. The absence of light prevents biological growth, such as barnacles or coral, which obscure and damage wrecks in the ocean. The silt itself is anaerobic, creating a seal around the lower surfaces of the airframe. The result is an object that appears almost exactly as it did the day it vanished. However, the depth imposes a different set of constraints through hydrostatic pressure. At roughly 74 meters, about 240 feet, the water adds just over 100 pounds per square inch of pressure, roughly 7 atmospheres above the surface. For a flooded airframe, this pressure is generally manageable because water enters and equalizes the load. Problems arise only where air remains trapped in a truly sealed volume, creating a pressure differential. In a slow sink through breaking ice, most spaces would be expected to flood and equalize on the way down, reducing the chance of dramatic structural collapse. That is consistent with glazing and canopy sections that can appear largely undistorted on a deep freshwater wreck. This environment created a deceptive target for the recovery team. The paint and markings could read as if the aircraft had been submerged for days, not decades, suggesting a structure ready to be lifted by standard hardpoints. But the lake's chemistry was never uniform across the airframe. While the aluminum skin looked preserved, critical joints and heavy fittings had been quietly changing for years. The visual evidence promised a solid lift, but the molecular reality had prepared a trap that would only trigger when the load was applied. The initial remote survey revealed it in light. As the inspection vehicle swept its beams across the fuselage, the aluminum threw back a clean reflection, the camouflage pattern still distinct beneath a veil of silt. The black cross markings remained sharp. On the side of the fuselage, the alphanumeric designator was clearly legible. Uniform 4 plus Tango Kilo. That signature confirmed the wreck as work number 0880119, matching the archival record from 1940. Then the sensors moved to the wing structures, and the image of preservation shattered. The Junkers Ju-88 was powered by two Jumo 211 inverted V12 engines. Each power plant displaces 35 liters and constitutes a significant percentage of the aircraft's empty weight. In a standard airframe inspection, these engines are rigidly bolted to the main wing spar. On the bottom of Lake Jonsvatnet, the engines of Uniform 4 were not aligned with the nacelles. They appeared to be drooping, or in some sections, entirely detached from the internal structure, resting independently in the silt. This anomaly was not caused by impact damage. It points to selective corrosion in an airframe built from dissimilar metals, often nicknamed magnesium rot, when magnesium-rich castings are involved. To save weight, aircraft of the era could use magnesium alloys in certain heavy fittings, including engine bearer structures and other cast parts. Magnesium sits far less noble than aluminum, so when the metals are coupled and immersed, the magnesium-rich pieces can corrode preferentially. Over decades, those parts may lose their strength and crumble into a chalky residue, leaving heavy assemblies like engines no longer properly supported by their original mounts. The airframe could still look deceptively pristine because cold, low-oxygen freshwater slows corrosion on many aluminum alloys, and burial in silt can shelter surfaces from abrasion and oxygen exchange. But that preservation was uneven. Over decades, vulnerable fittings and joints could fail while neighboring skins still carried sharp paint and markings. On this wreck, the heavy assemblies were no longer truly carried by intact, load-bearing mounts. The engines sat low, supported largely by surrounding sediment and whatever lines, cables, and plumbing remained, while the propeller spinners rested in the silt, dislocated from the thrust line. This reality forced an immediate revision of the recovery engineering. A standard lift often utilizes the engine mounts or landing gear trunnions as primary securement points because they are designed to carry the weight of the aircraft. In this case, those points no longer existed. Attempting to lift the WWII by its engines would result in the power plants tearing free, potentially unbalancing the fuselage or causing the wing structure to twist and fail. The integrity of the aluminum skin was a facade covering a structural void. The recovery team now faced a 65-foot wingspan that could not be grabbed by its strongest nodes. The primary hazard in recovering a submerged airframe is not the weight of the metal, but the grip of the sediment. Fine silt can seal against a fuselage belly and wing roots, resisting movement with forces that may rival the aircraft's own mass. When the seal breaks unevenly, the loads do not rise smoothly. They spike, twist, and concentrate, exactly the kind of stress a compromised structure cannot survive. If a lift is attempted with brute force, a weakened airframe can fail at its highest stress point, splitting the story into pieces. To neutralize this risk, the recovery team used a controlled breakout process to free the airframe from the lakebed before any serious vertical load was applied. Once the seal was relieved, the engineering problem shifted to lift geometry. With traditional attachment points compromised, the team needed a cradle that supported the wing roots and fuselage without squeezing the wings inward. A wide spreader frame kept slings vertical and loads distributed, transferring weight into the strongest structure near the center section instead of into fragile, corroded fittings. The lift itself was a slow, deliberate hydraulic operation. The crane took up the slack, verifying the balance. Slowly, the WWII separated from the bottom. The 18,000-pound load included not just the airframe, but tons of water and mud trapped inside the wings and fuselage. As the aircraft rose, pressure fell, so the ascent had to stay slow enough for trapped gases to expand and water to drain, preventing internal blowouts. The bomber rose through the darkness, held in the cradle of the lifting straps. It passed the thermocline, the water temperature rising slightly. Finally, the dorsal gun position broke the surface of Lake Jonsvatnet. For the first time since April 1940, the cockpit glass was exposed to the atmosphere. The physical recovery was complete, but the exposure to oxygen signaled the start of a new, urgent degradation phase. The protective stasis of the deep water was gone. The interface between the lake surface and the atmosphere represents a radical shift in environmental boundary conditions. After decades in low oxygen and constant pressure, the Junkers WWII crossed back into a world of variable temperature and high oxidation potential as the crane operator completed the lift in September 2004. This transition is not merely a visual milestone, it is a critical control point where the preservation strategy must pivot from retrieval to stabilization. As the water drained from the fuselage, the effective weight of the aircraft changed. The buoyancy provided by the lake vanished, transferring the full load of the structure to the lifting cradle. The 65-foot wingspan, still carrying residual silt and water in its cavities, had to be maneuvered onto the waiting recovery barge with precise coordination. For the first time since 1940, the airframe was experiencing full gravity bending without the cushioning support of the water, and it had to be set down cleanly, firmly seated in its transport jig before any new distortions could start. Once secured on the deck, the evidence of the deep water environment was visible. The aircraft was not covered in rust or marine growth. It was coated in a fine layer of gray silt. Underneath this sediment, the paint was preserved to a degree that is rarely seen in aviation archaeology. However, the exposure to the air immediately activated the corrosion clock. While the aluminum was stable, the steel fittings, control cables, and remaining iron components were now vulnerable to flash corrosion. The high oxygen content of the atmosphere, combined with the moisture remaining in the crevices, creates an ideal electrolyte for rapid oxidation. The decision at this stage was not to clean the aircraft immediately to bare metal. The priority was to keep conditions controlled and to arrest new reactions as the wreck transitioned from low oxygen water to open air. Corrosion inhibitors and careful handling bought time, while drainage and drying had to be managed so that coatings, residues, and vulnerable steel components did not flash, corrode, or deteriorate abruptly. Unlike saltwater recoveries where chloride removal dominates, the freshwater context allowed a more deliberate stabilization plan focused on oxygen exposure and moisture control. The engines, retrieved separately due to the failure of the magnesium mounts, were placed alongside the fuselage. These components required different treatment. The steel cylinder liners and complex internal gearing of the Jumo 211 power plants were far more susceptible to immediate degradation than the aluminum airframe. They were submerged in preservation tanks or treated with heavy oils to displace the water. With the aircraft stabilized on the barge, the operation shifted from a marine salvage to a logistical transport. The destination was not a scrapyard nor a remote storage facility. The aircraft was slated for the Norwegian Armed Forces Aircraft Collection at Gardermoen. This facility possessed the controlled climate required to slowly acclimate the airframe to a dry environment. The objective was to freeze the aircraft in time, preserving the specific history of its loss rather than erasing it through over-restoration. The journey from the lake to the museum would be the final leg of a mission that began with a takeoff on a frozen sheet of ice. The difference between a restored warbird and a forensic artifact is defined by the surface. A restoration often involves stripping away the history to create an illusion of the factory floor. The Junkers Ju 88 sitting in the Forsvarets Flysamling at Gardermoen tells a different story. It does not gleam with new paint. It wears the same camouflage pattern that was applied in 1940. The black crosses are not decals applied by museum staff. They are the original chemical bonds formed 64 years ago. This airframe is not a replica of the past. It is a direct physical witness to it. The primary objective of the recovery was to retrieve the aircraft without destroying this evidence. That objective was achieved. The fuselage code, U4 plus TK, remains clearly visible, tying this machine to the unit known as Ergänzungskampfgruppe 4 and reinforcing the historical record of chaotic logistics during the invasion of Norway. Its presence in the museum validates the archival data regarding the use of ice airfields as a tactical necessity. In the controlled environment of the museum hall, the aircraft rests in a disassembled state that reflects its recovery condition. The conservation philosophy chosen for this project prioritizes stabilization over cosmetic perfection. The aluminum skin retains the matte finish created by decades of immersion in cold freshwater. The silt that was carefully removed has revealed the industrial reality of 1940, including the stenciling on the fuel ports and the specific shade of the cockpit interior, details that differ from later production standards. The engines and the fuselage are displayed in proximity, but the scars of the lake chemistry are preserved. The point where the magnesium engine mounts dissolved is not hidden or reconstructed with modern metal. It is left as a gap. This void serves as a permanent record of the galvanic corrosion that occurred deep underwater. It demonstrates the interaction between the aircraft materials and the lake environment, teaching the observer about the metallurgy of the era and the specific constraints of the recovery. The magnesium rot is not treated as damage to be repaired, but as a signature of the site itself. The success of this operation lies in the discipline of the retrieval. By respecting the physics of the silt suction and the geometry of the lift, the team brought the airframe to the surface without introducing new trauma. The structural continuity that survived the sinking in April 1940 was maintained through the transition to the atmosphere in September 2004. Today, work number 0880119 stands as a rare surviving early Ju 88 airframe, remarkably intact for a machine that spent decades on a lakebed. It gives engineers and historians an unusual reference point for materials, layout, and wartime finish in an early production bomber. The aircraft is no longer a strategic weapon, nor is it a hazard on the bottom of a frozen lake. It is a stabilized document of aviation history, held in the controlled safety of the museum, protected from the elements that once claimed it.